Mastering Python Section 6, Coroutines and Asynchronous I/O. 6.1. Understanding why this isn't like parallel processing. In this video, we're going to take a look at the resource usage of parallel programs and the implications for server processes. When we were working with the concurrent.futures module, we saw a way to make two or more streams of code run at the same time. We could create an executor object, and then whenever we wanted to run code in parallel, we could tell the executor to run the code. The executor would give us a feature object that we could later use to get the result of the code, and it would then run the code in a separate process while our original code kept on running in our original process. We talked about how this could improve the performance of CPU-bound programs by letting the code be divided up between multiple computer cores, but it seems like a technique that could be convenient for a lot of other circumstances. It's handy to be able to tell the computer, "Go and do this, and let me know when you're done." One place where that ability seems particularly useful is network server programs, where having a separate stream of execution for each connected client makes the logic and structure of the code much easier to grasp, which means that it's easier to write bug-free servers when they're structured that way. There are ways to write a server that use only a single stream of execution, but if we have a way of writing servers that probably introduces fewer bugs, why wouldn't we? The problem is resource overhead. Every process running on a computer uses up memory and CPU time, of course. But in addition to the memory and CPU time it actually needs to run its code, the operating system also needs to expend resources to manage the process. As it happens, the time spent on switching between processes is significant. The memory overhead is enough that it becomes a limiting factor on how many clients a multi-process server can handle simultaneously, and other internal operating system resources may be even more limiting. For CPU-bound programs, there's a sweet spot that produces optimal results where the program has one process per CPU core. For an I/O-bound program, which most servers are, any process beyond the first is nothing but overhead. As I mentioned, there are ways to write single-process servers that can handle multiple clients at once. With much lower overhead per connected client, using these techniques actually allows a server to handle many more clients at once than a multi-process server program could. Even when not operating at full capacity, a single-process server leaves more of the computer's resources available for other uses. So, on the one hand, we have a way of writing servers that is logically structured and less prone to bugs, but wastes resources. On the other hand, we have a way of writing servers that is resource efficient, but easy to get wrong. Can we somehow get the best of both worlds? The answer is yes, fortunately. Python's standard Async IO module combines the low-level techniques that allow a single process to service multiple clients with a cooperative coroutine scheduler. The end result is a programming interface that looks and acts a lot like concurrent.futures, but with much lower overhead per stream of code execution. That's great, but what is a cooperative coroutine scheduler? For that matter, what's a coroutine? A coroutine is a computer science concept, a function that can be paused and resumed at certain places within it. Each time it pauses, it can send data out, and each time it is resumed, it can receive data. Python generator functions are capable of behaving like coroutines by using the yield statement as the pause and resume points, and Async IO takes advantage of that. A cooperative coroutine scheduler is a piece of code that picks up the execution each time a coroutine pauses, and decides which coroutine should get to run next. It's called a scheduler because it keeps track of multiple streams of execution and decides which one gets to run at any given time. It's called cooperative because the scheduler can't yank the right to be running away from a coroutine and give it to another one. It has to wait until the running coroutine pauses itself, and then it can select another coroutine to run. In Async IO's formulation of coroutines, the pause and resume points are yield from expressions, which are also how we call other coroutines. Each time we want to perform a function call on a coroutine from inside another coroutine, we yield from that coroutine we want to call. As far as the semantics of the code work, that behaves just like calling a function from inside a function. The other coroutine runs until it returns, and we get back the return value. That's how the code behaves, but what it actually does is quite a bit more. The first thing that happens is that the coroutine we're running is paused. The coroutine we want to call is handed off to the scheduler, which places it into a list of coroutines that need to be run. Then the scheduler checks to see whether anything has happened that a coroutine was waiting for, such as new data coming across the network or another coroutine returning, and if so, it adds the waiting coroutines to the list as well. Then the scheduler picks one of the coroutines that needs to run and unpauses it. That means that if a coroutine has a long-running loop that doesn't contain any yield from expressions, not only will it block any other coroutine from running, it will also keep the program from checking for new data coming in across the network, and prevented assorted other input and output operations from being serviced. If we have such a loop, and there's just no reason to call any other coroutines inside it, we can place a yield statement into the loop body, which simply gives the scheduler a chance to do its thing. The little bit of extra complexity that comes from needing yield from expressions and the occasional yield statement is the price of a cooperative scheduling. But since the payoff is efficient and logical code for I/O-bound programs, it's often worth it. So we've just seen an overview of how Async IO allows us to use the logical structure of a parallel program, while retaining the advantages in terms of code execution of a threaded single process program. This is advantageous for us when we're dealing with I/O-bound programs. In the next video, we'll look at using the Async IO event loop and coroutine scheduler.